In this presentation, we introduce SWAN, an open-source framework that allows robust analysis of Swift programs. My name is Daniil Tiganov, and SWAN is joint work by myself, Jeff Cho, Karim Ali, the three of us are from the University of Alberta, and Julian Dolby from IBM. The Android platform has had a lot of attention over the past decade from the static analysis community. Many static analysis frameworks have been developed, including FlowDroid, ScanDroid, and DroidInfer. However, there is no openly available equivalent counterpart for the Swift platform. This means there is no openly available security analysis tool for iOS or macOS applications written in Swift. Moreover, Swift has become Apple's recommended choice for development on iOS and macOS and has seen rapid development and growth. While this isn't discussed in the paper, I want to motivate the need for security analysis tools for Swift applications even further. I'll do this by talking about some vulnerabilities iOS applications are susceptible to. Apple is known for sandboxing their apps, so the types of security vulnerabilities in iOS apps is not necessarily obvious. InfoSec has determined that the various registries and stores available for iOS developers to store information in, such as user information, should not be used to store sensitive information like user passwords. These stores include user defaults, property list, and core data. Apple has other methods of storing information securely, such as through the keychain. A static analysis tool could detect when sensitive information is written to these stores and alert the developer that this is a security vulnerability. Cryptographic API misuse is another security vulnerability that static analysis has proven to be effective in. Java developers can use the CogniCrypt Eclipse plugin to make sure that they are using Java crypto APIs correctly. We believe Swift developers would appreciate similar misuse detection for popular Swift crypto APIs. These APIs include CryptoSwift, a popular open source API, and Apple's own API called Swift Crypto, which was recently released. Of course, there are general vulnerabilities, such as SQL injection or hard-coded credentials that static analysis could also detect in Swift applications. To bridge this gap between the increasing popularity of Swift, the lack of available static analysis tools, and the many security vulnerabilities Swift applications are susceptible to, we introduced SWAN, a static analysis framework for finding security vulnerabilities in Swift applications. First, I just want to briefly talk about what SWAN is and is not in its current state. Currently, SWAN only analyzes single Swift files. Xcode project support, meaning multi-file Swift, iOS, and macOS application support, is work in progress. At one point, we were able to analyze Xcode projects. However, recent changes to Xcode, Swift, and macOS versioning render our Xcode frontend non-functional. SWAN supports almost all of the Swift language, and modeling for Swift standard libraries is work in progress. That is, modeling data flow through standard library components such as containers. Lastly, SWAN supports taint analysis for user-defined sources and sinks. In order to achieve SWAN's goal of analyzing iOS and macOS applications, we are working on completing SWAN support for Swift, Xcode projects, and the Swift standard library. Now I'll explain SWAN's general architecture. SWAN has a couple of frontends, which will be demonstrated later, but these frontends essentially configure, run, and view the results of SWAN. The user's configuration options are given to the SWAN driver. SWAN uses IBM's TJ Watson Libraries for Analysis, or WALA. WALA is an established static analysis framework that has support for many languages including Java, JavaScript, and Python. The SWAN driver calls the WALA driver. The WALA driver does all of the WALA-specific API calls, including creating a WALA analysis engine. The WALA analysis engine requires a translator from the input language, in our case Swift, to its own representation. Therefore, we give the engine the SWAN translator. The SWAN translator needs some representation of Swift, and therefore uses the SWAN hook. SWAN hook is actually written in C++, because while SWAN and WALA are both written in Java, the Swift compiler is written in C++. Therefore, the SWAN hook programmatically invokes the Swift compiler directly. Now, SWAN doesn't actually analyze the Swift language directly. After extensive discussions with the Apple Swift team, we determined that it is best for SWAN to consume the Swift Intermediate Language, or SIL, which is Apple's internal IR for Swift, instead of the Swift abstract syntax tree. So this SIL is grabbed from the Swift compiler at runtime, and then passed back to the SWAN translator. The SWAN translator translates SIL to SWAN's own IR, SWAN IR, which I'll explain further shortly, and then SWAN IR is translated to cast. Cast is WALA's own AST, but is not WALA's final representation. Therefore, the WALA analysis engine translates cast to WALA's internal representation called WALA IR. And during that process, WALA does pointer analysis, SSA conversion, call graph construction, and so on. At the end, WALA outputs a call graph object, denoted CG, which contains the whole program in WALA IR form. The WALA driver then uses WALA to construct a system dependence graph, or SDG, from the call graph. The SDG is a WALA data structure that represents data flow of the program. So if you want to track a value through the program, for instance, that is a simple graph reachability problem over the SDG. The SDG is passed back to the SWAN driver. The SWAN driver then gives it to SWAN's custom client analysis, which is taint analysis in this case. The taint analysis finds paths from sources to sinks in the SDG, and then ultimately gives the results of the taint analysis with source information back to the front end, where the results are displayed to the user. Now I want to further explain how the SWAN Translator works, since the translation from SIL to WALA IR is complex. For example, SIL has over 160 instructions. So to reiterate, we begin with the Swift intermediate language, translated to SWAN IR, then to cast, and then finally WALA translates cast to WALA IR. Translating SIL to SWAN IR is the most complex part of the translation process. For instance, WALA IR, and naturally by extension SWAN IR, is a reference-based representation, while SIL is a pointer-based language. Therefore, pointers are converted into references through a technique called field aliasing. WALA also doesn't support coroutines, so SIL's asymmetric coroutines are inlined. Built-in function models are injected, so for example we have modeled some Swift container functions with SWAN IR. And lastly, minor things such as ignoring data flow irrelevant instructions, which greatly reduces the amount of instructions that we need to translate to SWAN IR. We designed SWAN with the app developer as our main target audience, and therefore usability was a priority. SWAN provides both a command line interface and a graphical user interface in the form of a VS Code extension. I'll demonstrate the command line interface first. However, before I give a demonstration of SWAN using SWAN's frontends, I need to explain the code example SWAN will run on. At the top of the example, you can see there's a source and a sink defined in a comment format, which is necessary for configuring SWAN's command line interface frontend. Then we see our source and sink function. Next we have two classes, class A, which has a field G of type B, class B, which has two fields, F and V, both of type string. Then we have a function called syncfunc, which returns our sync function as an object. This is to show that we support Swift's function objects. Then we have a function called foo, which takes in a value of type B and a string. It concatenates that string with a static string and then writes it to the field F of B. And then here's actually where we use all of those classes and functions. So first, we create an object of type A. We assign the G field of A to the object B. We then create another object of type B. We create a tainted string. We pass that string to foo, where it's written to b.f, so that is after line 45, b.f should be tainted. We then create a function object representing our sync function, and then we call it with b.f. So we should detect a vulnerability at line 48 because b.f is tainted and f represents the sync function object. We also sync the other field of b to show that we have field sensitivity, that is, we can differentiate between fields. We also sync the other object that we created just to show that we have object sensitivity, that is, we can differentiate between instances of the same class. Here I'm running the command line interface tool on the code example I explained earlier. All I need to do is give it the macOS SDK path and the path to the Swift file being analyzed. SWAN will dump lots of information, but all we really care about are the results at the end. So here we can see that SWAN found a dangerous path for the program. It displays the path using nodes. Each path begins with a source node, can have intermediate nodes, and ends with a sink node. Each node contains source information too. I'll label these nodes so we can compare them with the code example. So let's bring in that code example. Beginning with the first node, the source node, we can see that a source is being created on line 44. Then that tainted variable is passed to the function foo on line 45, so that node would represent the caller node, and then the third node represents the callee node, where that tainted value is received. The tainted string is then concatenated and written to b.f, and then later on line 48, b.f is sunk. So this is consistent with what we discussed earlier, that is, we properly detect the path. Now we'll demonstrate the VS Code extension frontend. Let's first take a look at the configuration options. Like with the CLI tool, we need to specify the SDK and the Swift file path. I have already configured these. To configure sources and sinks, we need to add them in the settings.json. We can take advantage of SWAN's source and sync autocompletion if we first compile the Swift program by running the analysis. Sources and sinks can be defined before first-time analysis, but for demonstration purposes we will use autocompletion. We can run SWAN by navigating to the SWAN tab and using the menu in the sidebar. When running the analysis for the first time, SWAN will look to see if there is a SWAN server already running, since it is possible to start SWAN separately. In this case, it doesn't find one, so it starts a new analysis server. Now we have run first-time analysis, we can use autocompletion to enter the sources and sinks defined in the test case. Let's rerun the analysis. Here we can see that we have detected a dangerous path. We can click on the path nodes in the tree view to view them in the source file. We can see that these are the same paths we went over in the CLI frontend. So let's modify the source code to show how quickly SWAN can reanalyze it. I'll just sync b.f again, which should result in a similar path to the first. As expected, we now have two paths. We can now stop the analysis server to conclude the demonstration. SWAN is still work in progress, and there is a lot to do yet in order to achieve SWAN's goal of analyzing Swift applications, especially for iOS. Therefore, I'll say a little bit about the future work we have planned and what we're working on right now. First, we want to move away from hooking into the compiler and grabbing the SIL at runtime, by instead parsing plaintext SIL. This should enable support for Xcode projects, and by extension iOS and multi-file Swift apps. We will also need to complete Swift language support, so this includes the base language and Swift standard libraries, so that we can have most of the data flow modeled. We want to develop a robust client analysis for detecting security vulnerabilities, so this includes identifying sources and sinks for various vulnerabilities. And we also plan on exploring API misuse detection. Thanks for watching this presentation. If you would like to learn more, please visit this link.